Hi everyone, this is the last video for your second chapter, that is the structure of an atom. In previous classes, we are studied about thoroughly all the concept of this chapter. In today's class, I wish to revise some main concept of this chapter, that is the structure of an atom. The understanding the concepts is very important to you. How this is important to you? Like that, the revision of every chapter is also important to you by the point of examination. So I wish to give the summary or the small revision about this structure of an atom, guys. Atoms are the building blocks of the elements, means the thing or the matter or the object which is surrounded by you, all made up by atoms. First we read the definition of atom like this. The atoms are very smallest particle and it is indivisible. But at the 19th century we got the real definition of the atoms, like the atoms are divisible and consist of three fundamental particles. Those fundamental particles are electrons, protons and the neutrons. The electrons are discovered by the J.J. Thomson with the help of the experiment cathode ray discharge tube, and these electrons are carry the negative charge, and the charge on the electron is minus 1.6 into 10 raised to minus 19 coulomb, and the mass of the electron is 9.10939 into 10 raised to minus 31 kg. And next one is the protons. The next fundamental particles are protons, and these protons are discovered by the E. Goldstein with the help of the experiment modified cathode ray discharge tube, and these protons carry the positive charge, and the charge on the protons is plus 1.6022 into 10 raised to minus 19 coulomb, and the mass of the proton is 1.67262 into 10 raised to minus 27 kg. And next one is, the next fundamental particles are neutrons. This neutron is discovered by the James Chadwick with the help of the experiment by bombarding the thin sheet of beryllium with the alpha particles. Then we know the existence of the neutrons, and these neutrons carry a zero charge. Remember, electron carries negative charge, protons carries positive charge. Neutrons don't have any charge, like a positive, like a negative. So it carries a zero. And next one is, many of scientists came and give their ideas about the structure of an atom. So first, the Thomson model of an atom. Thomson gives his ideas about the structure of an atom. He says atom is a sphere, and in that sphere uniformly distributed positive charge with a number of electrons are distributed in like a watermelon. Like a watermelon, he says atom is a spherical and the positive charge is uniformly distributed throughout this atom, and the electrons are embedded into it, distributed into it. So this model is also referred or also called as a watermelon. And next, some fact the Thomson fails to explain about the structure of an atom. So the Thomson model theory fails, and next scientist will came and give his ideas about the structure of an atom. So that model is Rutherford's nuclear model of an atom. So he also says the atom is spherical in a shape, and he says in that atom, so see here, in that atom some mass is concentrated at the center of this atom, and that mass is called as a nucleus. So he says about the nucleus. And next what he says about the orbits, means the electrons are revolve around the certain path or certain circular path. So this path are called as an orbit. So atom exists like this, he says to us. And next, nucleus and electrons are having or hold together with the help of electrostatic force of attraction. With the help of electrostatic force of attraction. So this is the idea of the structure of an atom according to the Rutherford. He says about the nucleus, it is very small and in between there is large space and electrons are revolve around the nucleus in a certain circular path, and that path are called as an orbit. But once he fails to explain the facts, some facts about the structure of an atom, like he says us the electrons are continuously revolve around the nucleus. But according to the Maxwell, what happened when charged body moves around the nucleus, it get accelerated and it emits the some energy in the form of electromagnetic radiation. It lost the energy and surrounding the nucleus, it lost the energy and it falls on this nucleus and then atom will be collapsed. So this is not happened in an atom. So it is the drawback of Rutherford's model of an atom. He fails to explain this fact about the atom. Then the Rutherford's model of an atom also fails to explain the structure of an atom. And next theory will become like a Bohr's model of an atom. Before we are going to study about or to revise about the Bohr's model of an atom, we have some terms are there like atomic number, mass number, isobars and isotopes. What do you mean by the atomic number here? Atomic number is nothing but the number of protons in a nucleus is equals to number of electrons in the nucleus. So what do you mean by the atomic number? Atomic number is denoted by the Z. The number of protons in the nucleus is equals to the number of atomic number, and the number of electrons in the neutral atom is equals to the atomic number. For example, we are having a 6 protons in a carbon, 6 electrons in a in this carbon atom. And next we are having the atomic number 3 to the lithium. Lithium plus we are having a 2 atomic number. Why? In the neutral atom of this lithium we are having a 3 proton, 3 electron. But in a lithium plus we are having a 3 proton but 2 electrons. So atomic number is equals to the number of electron and it equal to the number of proton when only atom exists in a neutral state. So this is called as an atomic number. And what do you mean by the mass number? The number of protons plus the number of neutron is called as an mass number. Next one is isobars. The atoms with the same mass number. So these are the atoms. So see here, carbon and nitrogen are the atoms. These are atoms with the same mass number but different in their atomic number. So this type of an atoms are called as an isobars. And next one is isotopes. So isotope is nothing but the atoms with the same atomic number. So see here, these are the atomic numbers. The atoms with the same atomic number but different in their mass number is called as an isotope. So this is the isotope of hydrogens like a hydrogen, deuterium and the tritium. Observe here, these hydrogens are having the same atomic number but different in their mass number, called as an isotopes. And next come with the Bohr's model of an atom. This Bohr's model is developed with the help of 2 points like dual character of electromagnetic radiation and the atomic spectra. So what do you mean by the dual character of electromagnetic radiation? Just remember it? Yes, that is right. The dual means double, means the electromagnetic radiation is behave like a wave and the electromagnetic radiations are behave like a particle also. With the help of these 2 points means the atomic spectra. What do you mean by the spectra here? When you pass the white light through the prism, then what happens? It splits into different colors according to their wavelength. So this is called as a spectra. So this spectra we get by the atoms or by the molecules. When we are give the extra energy to that atoms and to that molecules, then we got the spectra that is called as an atomic spectra. With the help of this atomic spectra and with help of this dual behavior of an electromagnetic radiation, the Bohr developed his model. So by the help of electromagnetic spectrum, we know more about the wave nature of the electromagnetic radiation or the electromagnetic waves. In this electromagnetic spectrum, according to their frequencies or according to their wavelengths, in different regions, the different electromagnetic radiations like gamma rays and X-rays, UV rays, infrared rays, visible region, microwaves, radio waves. So like this, different regions of electromagnetic radiations are present in the different regions according to their wavelength and frequencies. So by studying this electromagnetic spectrum, we know about the wave nature of the electromagnetic radiation. And next, there are two experiments to know the particle nature of the electromagnetic radiations also. By the help of black body radiation and the photoelectric effect. So by observing the results of these experiment, we more clear about the particle nature of the electromagnetic radiation. So what do you mean by black body radiation here? So black body radiation is nothing but a perfect body. It absorbs all radiation incident on it. So consider this is one body, this is our black body. It absorbs all incident light falls on it. So this is called as a black body radiation. When the black body radiation is heated, then what happens? Some radiations are emission from that black body radiation. So the nature of emission of radiation from hot bodies, then we know some results. By that results, we conclude the particle nature of the electromagnetic radiation. So the energy is equals to h mu. H is the Planck's constant. The value is 6.626 into 10 raised to minus 34 joules second. So this is the Planck's constant and this is the frequency. So energy is directly proportional or is equals to Planck's constant into frequency. And the next one is photoelectric effect. What do you mean by photoelectric effect here? So this is two metal surfaces. One is a detector and it is a photosensitive material which is well responds to the light. So this is our glass tube. This is our glass tube. These are connected with the wires. One is a negative end, another one is with a positive end. When the source of light made a falls on this photosensitive material, this metal, then what happened? This metal eject the electrons. The electrons are outcomes from this photosensitive material. So this effect is called as this phenomena is called as a photoelectric effect. So photoelectric effect is nothing but the ejection of an electron from the metal surface when the radiation strike on it. So by the help of the photoelectric effect, we know the particle nature of an electromagnetic radiation. How? So see here, we observe these results by the help of photoelectric effect. So what are those results? I will discuss here. There is no time lag between striking of light beam and the ejection of electrons from the metal surfaces. I already told you when we made the light falls on this surface, then the ejection of an electrons takes place. When you made fall or when you incident the electromagnetic radiation on the metal surfaces, at that moment only, without time gap, the electrons are ejected from this metal surfaces. And next one is the number of electron ejected is directly proportional to the intensity of light. So see here how much intensity of light we have to made fall on it. So what is the intensity? If the intensity is less, the ejected electron is less. If we made the intensity of light is high, then the ejected electrons numbers also high. So the number of electrons ejected is directly proportional to the intensity of a light. And next one, for each metal there is a characteristic minimum frequency that is called a threshold frequency. I already told you there is a certain minimum frequency is there. By that frequency only we incident the electromagnetic radiation on the surfaces with a certain frequency. So consider the 50 hertz. 50 hertz is a threshold frequency. When your electromagnetic radiation has the frequency 50 hertz, then only the ejection of electrons takes place and the photoelectric effects takes place. If we got a 40 hertz, we can't reach our minimum threshold frequency. Our minimum threshold frequency for this metal is 50 hertz, but we apply 40 hertz. When we apply a 40 hertz for this metal, then there is no observation of the photoelectric effects takes place. When we apply the minimum frequency, means the threshold frequency to this metal through the help of this electromagnetic radiation, then only we observe the photoelectric effect. So this is called as a threshold frequency. If we apply 100 hertz frequency here, if we apply 100 hertz frequency here, then what happened? This metal surface use this threshold frequency and another 50 hertz frequency of that electromagnetic radiation. These electrons are absorbed and they got a certain amount of a kinetic energy. Our threshold frequency is used for photoelectric effect and the remaining frequency is converted as kinetic energy of that electrons. So like this. See here, for each metal, different metals have a different threshold frequencies. For each metal there is a characteristic minimum frequency is there. So this frequency is denoted by mu naught, and this is if the applying frequency, mu is our applied frequency, mu naught is a threshold frequency. Our applied frequency is greater than the threshold frequency, then what happened? Electrons can come out with a certain kinetic energy, As the high frequency we applied the electromagnetic radiation on it, we got high kinetic energy of electrons here. As mu increases, kinetic energy of electrons also increases. With the help of these results, we conclude the particle nature of electromagnetic radiation. By observing this photoelectric effect and the black body radiation, finally we concluded that whenever light interacts with a matter, it displays a particle-like properties, or it shows a particle-like properties. So this is a matter, this is a light, or this is a matter, this is a light. When the light is interact with this matter, then how the electromagnetic radiation behaves as particle. When the emission of an radiation takes place, when the absorption of an radiation takes place, when the lights are interact with a matter, that emission and in that absorption, the electromagnetic radiation behaves as a particle. And next, when the light is in a propagation way, when the light is moving, then it behaves as a wave like. So it is proven in the experiment of interference and the diffraction. By the help of interference and by the help of diffraction, which exhibits when it propagates, when the light is in a propagate state. So in this experiment, the light is in propagation state. So when the light interact with the matter at the time of emission, at the time of absorption, then the light behaves as a particle. When the light is in a propagation state, in the interference and in a diffraction, then we observe the electromagnetic radiation behaves as a wave. So finally we conclude the particle nature of electromagnetic radiation and the wave nature of electromagnetic radiation. Then the Bohr studied about thoroughly the hydrogen line spectrum. Before we are moving to hydrogen line spectrum, we should know about the atomic spectra here. So this atomic spectra gives us the evidence for the quantized electron energy levels. So quantized means some particular values, those are available to us. So like 1 rupee coin, 2 rupee coin, we don't have 2.5 rupee coin. So the coins are quantized, they are available particular values. So like that, the energy levels are also quantized in nature, and this evidence is gives by the help of this atomic spectra. So what do you mean by the atomic spectra here? We got a spectra by the help of atoms. When we apply the energy, so these are our atoms. When we apply the energy, then what happened? The electrons absorb the energy, and these are jumps from lower energy to higher energy level. In the higher energy level, they are unstable. In the higher energy level, they are unstable. So to become a stable, again they are lost their energies in the form of a radiation. So this radiation, when we pass this radiation through the prism, we got a spectra. So this is called as an atomic spectra. So atomic spectra are two types, the emission spectra and the absorption spectra. So what do you mean by the emission spectra and the absorption spectra here? Emission spectra is nothing but I already explained you. When we apply the extra energy to this atom, then what happened? Electrons absorb that energy and they jumps from higher level, and they are unstable in their higher level. Again they emits the radiation, they lost the energy, and again they come back to their original position. So with the help of these emission radiation, with the help of these radiation, we got the spectra on this photographic plate called as an emission spectra. We got a emission spectra with the help of a dark line, with the help of dark lines. So that's why we called as an emission spectra, called as well as a line spectra also. And next, what do you mean by the absorption spectra? So see here, you take one container, fill that container with the hydrogen gas. When we heat the hydrogen gas, then what happened? That the hydrogen atoms absorb some energies, and the remaining radiations comes out. With the help of that radiation, we got the spectra here. Then this is called as an absorption spectra. Absorption spectra. He thoroughly studied about the hydrogen line emission spectra here. So when we apply the external energy to this hydrogen atoms, then what happens? The electrons are absorb that energy and they are jumps from higher energy levels, and again they emits the radiation. They come back to its original position. So at this phenomena we got some line of series in a spectra. So like this, these are our energy levels, and these energy levels are denoted as a n is equals to 1, 2, 3, 4 and 5 like this. So this is the ground state of this electron. When we apply the energy, then what happened? It goes to higher energy level. Again there comes their original level from different energy levels. So like this, we got some set of series like Lyman series, Balmer series, Paschen series, Brackett series and Fund series. So Balmer series is a visible regions to us. Here we observe the lights like red, blue, yellow. So this visible region, in this visible region we got the Balmer series. So these lines of series are expressed in terms of a wave number, that is 109677 into 1 by n2 square minus 1 by n1 squared. So this is the lower region and this is the higher region. So see here, n is equals to 1 for this Lyman series, n1 is equals to 1 for the Lyman series and n1 is equals to 2 for the Balmer series, n1 is equals to 3 for the Paschen series. Means in the Paschen series the electron's ground state is third energy level. So n1 is equals to 3 in the Paschen series, n1 is equals to 4 in Brackett series. So like this n1 value is differ from line to line. So these are emission spectra, or these emission line spectra is used in chemical analysis to identify the unknown atom, because every element has a unique line emission spectra. How we match the fingerprints to identify the criminal, because every person have their different fingerprints. So like this, every element also has the different line spectra, and this spectra is matches with the unknown atom, and we find or we identify that unknown atom. So by studying these atomic spectra and the particle nature and the wave nature, finally the Bohr gives their postulates a well developed idea about the structure of an atom here. So what is the postulates of Bohr's model of an atom? See here, Bohr also says the electrons are revolve around the nucleus, and Rutherford also says the electrons are revolve around the nucleus. But what is the different? What he says, see here, electrons are revolve around the nucleus without changing its energy with respect to time. When the time changes, then according to with respect to that time, the energy is not change. The energy not change in that electron. So first postulate is the electron revolve around the nucleus without changing its energy with respect to time. And then the second formula he says to us, the frequency of radiation absorbed or emitted while transaction occurs between the two stationary states. I already told you when I explain about the spectra, the atoms are absorb the outer energy, higher energy, then only they jumps from lower to higher energy. Then what happens? The radiation comes out and they come back to its original position. So then only the transactions takes place between in two different lines or two different energy levels. So that energy levels are also called as stationary states. It is denoted by this formula, mu is equals to delta E by H. So here the delta E is E2 minus E1. the difference between energy of their energy levels. And next formula is the angular momentum is quantized and is equals to the integral multiple of h divided by 2 pi. So what he says, electron have a certain kind of angular momentum, and that angular momentum is quantized, means they available in a particular values. So what that values? Integral multiple of h divided by 2 pi, means angular momentum of an electron is, we got like this, 1h divided by 2 pi, 2h divided by 2 pi, 3h divided by 2 pi. We don't have 1.5h divided by 2 pi. We don't have this value because this is a quantized angular momentum of an electron is equals to integral multiple of h divided by 2 pi. So these are the postulates which is given by the Bohr's. By help of this hydrogen line spectra and the Bohr's model, we got some formulas to calculate the energy of that energy levels and radius of that atom, and next wavelength, wave number. So these are 3 formulas, just if have to remember, and these are helps to in your numericals. An is equals to minus 2.18 into 10 raised to 18 z square divided by n square into joules. Z is the atomic number of an hydrogen, N is their energy levels or principal quantum number, and Rn 52.9 n square is the energy levels divided by Z, means the atomic number of an hydrogen picometer here. And next, the Rydberg formula for hydrogen like atom is equals to 1 divided by lambda, or wave number is equals to r into 1 divided by n1 square minus 1 divided by n2 square into z square. Z is nothing but the hydrogen, means its value is 1 only. So what do you mean by the Rydberg? Rydberg is a constant, its value is 109677 per centimeter. So this is the value for Rydberg constant. And next, at a certain point, Bohr also fails to explain the structure of an atom, and the next theory will come, that is the quantum mechanical model. Quantum mechanical model. So where the Bohr fails to explain the structure of an atom. Limitations of Bohr's theory. The Bohr theory only explain about the hydrogen like atoms like a lithium plus and a helium plus. So like this single electron system atom only he can explain the structure of an atom and about the spectra. He can't explain about the multi-electron system like a helium, lithium, carbon, boron, beryllium, etc. So here he fails to explain the structure of an atom. And next limitation is he can't explain about the G-man effect. So what do you mean by the G-man effect is the splitting of spectral lines. Splitting of spectral lines in magnetic field. The splitting of spectral line in a magnetic field is called as an G-man effect. So why in the magnetic field the spectral lines are splits up? So what is the meaning of that splitting line? He can't explain in his theory, and he can't explain about the Stark effect also. Stark effect also, what is the meaning of the Stark effect? The splitting of spectral line in an electric field. When we put the spectral lines in an electric field, then also they got splits. So why the splitting of that spectral lines are happened in the electric field, means the Stark effect. He can't explain about this fact also. And next, he can't explain the ability of atom to form the molecules, how the atoms are combined with each other and how the molecules are formed. He can't explain about this point also. So these are the limitations of Bohr's theory. And next theory I already discussed with you, that is the quantum mechanical theory. And this quantum mechanical theory is a purely a theoretical science. So in up to this we studied about the classical method. So this is a classical science. So next theory is the quantum mechanical. So that is purely the mathematical based science, and it is a very theoretical science. So by this we got a clear structure about the structure of an atom. So this mechanical theory also built with the help of 2 points, that is the dual behavior of matter and the Heisenberg uncertainty principle. With the help of these principles, the quantum mechanical theory is developed to find the structure of an atom. So dual behavior of matter means matter also have a dual nature, like a wave nature and a particle nature. Every matter has a dual nature. So this is applicable lot of only a microscopic level particles like a electron and alpha particles. So these are behave like a particle and these are behave like a wave. We can observe two properties in this microscopic level of a particle. So the macroscopic level particles also have the wave nature and the particle nature, like this board and marker. These are also have the particle nature and the wave nature, but the particle nature only considered, the wave nature is very small and it is negligible in the macroscopic level particle. So to prove the dual behavior of a matter, one scientist came. His name was de Broglie. His name was de Broglie. He gives a very beautiful equation to us regarding to the dual behavior of a matter. He connected the wave nature of a matter like a wavelength and the particle nature of the matter like a momentum. So the wavelength is universally proportional to this momentum. I can write h divided by p. Momentum is mass into velocity. So this is the de Broglie equation which is given by this de Broglie regarding to the dual behavior of a matter. Just remember, it is the lot of numericals asked on this formula also. And next, the Heisenberg uncertainty principle. This principle gives us a lot of information to develop the quantum mechanical model. So in a Bohr's model of an atom and Rutherford model of an atom, we studied there are a definite circular paths are there. The electrons are revolved in that path. Means it's easy to determine the position and the path of this electron. But it can't happen. We can't determine the position. We can't determine the momentum of an electron simultaneously. Why it happened? Because there is no definite trajectory path. So this big matter or this big information gives by the Heisenberg. So what the Heisenberg uncertainty principle says us? See here, it is impossible to determine position and momentum of electron simultaneously. So this is the statement of Heisenberg uncertainty principle. Impossible to determine position and the momentum of the electron or velocity of the electron. So this principle eliminates the information about this trajectory paths. This is eliminate the trajectory path. There is no definite circular paths around the nucleus because we can't find the position and the momentum simultaneously. If the paths are there, we can easily find the position, but not happen like this. So this Heisenberg uncertainty principle is mathematically right as delta x into or the product of delta p is greater than or equals to h divided by 4 pi. So this is the mathematical representation of Heisenberg uncertainty principle. X is denoted, or X tells to about the position, or the position represented by the X, and the momentum is represented by the P. The product of this change in position or error in position, change in momentum or error in momentum is greater than or equals to h divided by 4 pi. So this is the Heisenberg uncertainty principle. And next, with the help of these dual behavior of a matter and the Heisenberg uncertainty principle, quantum mechanical model is developed. For the system like atom, or a molecule, we got one equation named as a Schrödinger equation. That is h into psi is equals to E into psi. So the psi is where the psi is a wave function. So this wave function represents the orbital. These are orbits. The definite circular path called as an orbit. So what do you mean by the orbital here? The space surrounded by the nucleus. So this is the space surrounded by the nucleus is called as an orbital. Orbitals are different in sizes, different in shapes, and different in their energy in different atoms, in different molecules. So see here, next come to this equation. Here h is represented as, it is a one mathematical operation like your multiplication, addition, division. So like that, the Hamiltonian is also a mathematical equation. Hamiltonian operator on psi. So Hamiltonian operator nothing but the partial double differentiation of this wave function. So when we are solving this Schrödinger equation, we got one equation. So by the help of that equation, or we put some constant values in there, then we got the values of the position of electron and the behavior of electron, or where exactly the electron is present in that atom. So we know all these kind of information by the help of that equation. We are having a 4 set of quantum numbers. We are having 4 set of quantum numbers. So with the help of these quantum numbers, we find an address of electron. So quantum number gives address of electron. So where exactly the electrons are exist or present in this atom. So what are those 4 set of quantum number? Principal quantum number, and it is denoted by small n, and its value is 1, 2, 3, 4. This principal quantum number mainly talk about the main shells of atom, and named as K, L, M, N. Like, so this is a 1 shell, means K shell. This is 2 shell, L shell, 3 shell, M shell, and 4th shell. So this is 3rd shell, and this is the 4th shell, N shell. So like this, the principal quantum number denoted by the n. This talk about the main shell of electron, and this talk about the energy of an atom also. How the shells are increased in that atom, then the energy of that atom also increases. And the second quantum number is azimuthal quantum number. Azimuthal quantum number, and it is denoted by L, and its value is start from 0, 1, 2, 3. So this talks about the subshell of atom. So what do you mean by the subshell? In the main shell, again we are having, so consider this is our main shell. Here again we are having some cells, so these are called as a subshell. So the subshell having the orbitals. So see here, azimuthal quantum number L is equals to 0, 1, 2, 3. This is also talk about or says about the energy of an atom. The subshell of atoms are namely or denoted as SPDF. S subshell means the value is 0. If our value is 1, the subshell name is P. If the value is 2, the subshell name is D. So this is about the azimuthal quantum number. And the third quantum number is a magnetic quantum number. A magnetic quantum number. I already told you, Bohr says as the electrons revolve around the nucleus in a certain circular path, and he says this electron is behave as a particle here. But Heisenberg says electron is not revolve around like a particle, it revolve around in a three-dimensional in the form of wave nature. So the wave nature means it is revolve in a three-dimensional. Three-dimensional means there is a different axis or different coordinates and different orientations are there. Means like x-axis, like y-axis and z-axis. So like this, the magnetic quantum number says about the orientation, and it's talk about orbitals. The magnetic quantum number is denoted by ML, and this magnetic quantum number value is minus L 0 to plus L. Means if we are having the L value is equals to 1, then the ML value is plus 1 0 minus 1, or minus 1 0 plus 1. If our ML value is 2, then what happen? Plus 2, or you can write like this also, minus 2 minus 1 0 plus 2 plus 1, sorry, plus 1 plus 2, plus 1 plus 2. So we got 5 orbitals here. Here we got 3 orbitals. L is equals to 1 means P. Our P has 3 orbitals in 3 coordinates like Px, Py, Pz. Their value is plus 1, 0, minus 1. So like this. Or plus 1, 0, minus 1. So I write as a plus or minus 1 or plus or minus 1 here. Here if ML value is 2 means 2 is represent as D subshell. So D subshell are having the 5 types of an orbitals like dxy, dyz, dx square minus y square and dz square, dx into z. So like this we are having 5 types of orbital in D subshell. So this tells about the magnetic quantum number. Just consider here, in the atom we are having a nucleus, and surrounding that nucleus we have some certain space. In that space we are having the main shell represented at 1, 2, 3, 4 K, L, M, N shell, and this main shell have the subshells represented as a S subshell, P subshell, D subshell and F subshell, and in that subshell we are having the orbitals. So these are the orbitals px, py, pz or dxy, dyz, dx square minus y square, like this. We are having the different types of orbital. And next one, fourth one is the spin quantum number. Spin quantum number. So this spin quantum number says us the spin of electron. Spinning of electron means the electron revolve around the nucleus and that electron revolve around their own axis like this. So this is called as a spin. And these electrons revolve clockwise direction and the anti-clockwise direction also, and the spin quantum number values are plus half and minus half. Electron may revolve around the plus half or clockwise direction or anti-clockwise direction. So we represent the electron spin in terms of this symbol also, and the values are plus half and minus half. So these are all about the quantum numbers, and these quantum numbers gives an address of an electron. So just I wish to explain by one example. If our electron value is 2p. So what is the meaning of this 2p? This electron is in second main shell. This electron is in second main shell, and p subshell means p value is 1, and it has a 3 orbitals like a px, py, pz, and they are, so if I write 2p3, they are having clockwise spin like this. So this type, the address of an electron is given by this quantum numbers. And the next one, I wish to explain about the shapes of an orbital. I already told you orbitals are having the different shape, different size and different energies according to their atom. So what are the shapes of orbital? The next one is the shape of orbital. Shapes of orbital. So these shapes of orbital is decided by electron density. Means in a s orbital, this is our nucleus, we find the electron density, or we find the density, probability of density like this. Means this density is equal in all direction with respect to this nucleus. Then we decide the shape of s orbital is spherical in shape. Like this, we got the probability of density in a p orbital in dumbbell shape. Right? Dumbbell shape. Consider this is our z axis and this is our y axis and this is our x axis. So means we have the orbital in pz orbital like this. On the z axis, we got the probability of density in dumbbell shape. So the p orbital have the dumbbell shape, s orbital have spherical shape. So this is our pz orbital, this is x and this is y, this is our py orbital, and next this is our x and this is our y. We have a px orbital like this. This is our px orbital, py, pz. So these three are different coordinates. P orbitals have their dumbbell in shape. And next, In a d orbitals, we are having a totally 5 d orbitals. D orbital is dumbbelled in shape. Dumbbelled in shape. So this is all about the shapes of an orbital. So when we find the density, in between that density and this nucleus, there is some empty space is there, and that empty space where there is no probability of a density. So that space is called as a nodes. In this nodes, we are having a two types of nodes, means radial nodes and angular nodes. Angular nodes we got in a p orbitals and d orbitals. Radial nodes we got in s orbital. So this radial node is calculated by using the value n minus l minus 1, and the angular nodes are calculated by the value n, and total nodes calculated n minus 1. So these are the formulas for calculate the nodes in different orbitals. And next, how the electrons are filled in these orbitals. How they are filled. So we are having totally some rules to find how electrons are filled in their orbitals. So first rule is Aufbau principle. What the Aufbau principle states as? In a ground state of an atom, so this is our atom, so just consider this is our ground state, our atom is here, our electron is here. In a ground state of the atoms, the orbitals are filled in the order of their increasing energies. So this is our first orbital, consider this is our next orbital, consider this is our another next orbital. So this orbital have the energy 1 joule, just assume, and this or electron volt or joule, 1 electron volt, and this orbital have the energy 2 electron volt, and this orbital have a energy 3 electron volt. Just assume, it's a general example. First the electrons filled in this orbital only, which having a low energy, and next the electrons are filled in this orbital, next the electrons are filled in this electron. If you are having consider a lithium, we are having a 3 electron, and consider a carbon, we are having a 6 electron. So here 3 electrons are first fill 1 electron here, and next electron here, and next electron filled here, and the next electron filled here. So I wish to denote or named their energy levels 1s, 2s, 2p, 3s, 3p. So these are the energy levels, increasing their order of their energy levels, increasing order. I write here, increasing order of their energy level. We fill maximum 2 electrons in a s orbital. We fill maximum 6 electron in a p orbital. So see here, I have 3 electrons. First I wish to fill s orbital, and next another remaining will go in this second energy level. Means 1s has a less energy than the 2s. First electrons are filled in a 1s, and next they are filled in a 2s. Next they are filled in a 2p, and next they are filled in a 3s. So like this, the electrons are filled their orbitals with increasing order of their energy levels. So this states the Aufbau principle. And next one is the Hund's rule. So this Hund's rule states about the multiplicity of the electron. So consider in the p orbital and the d orbital, we are having in the p subshell and in a d subshell we are having 3 orbitals. So these 3 orbitals and these 5 orbitals are degenerate. Degenerate means in the same subshell, means in the same energy level we are having a different orbitals. So these px, py, pz, so these are lie in same subshell, means these are exist in a same energy level but they are a different orbital called as a degenerative. So like this degenerative orbitals, how the electrons are filled, how the multiplicity of electrons takes place, this says about, or this says a Hund's rule. So see here, the pairing of electron in the orbitals belonging to the same subshell like a PDF doesn't takes place until each orbital belonging to the subshell has got a 1 electron. First we fill a 1 electron in these orbitals. When all orbitals are filled by each electron, then only the pairing will be start. Here another condition is that the filling of each single electron must be in a same spin. They are not filled like this in a different spin. They must be in a same spin or same direction. See here, we filled like this. And next I wish to give one example here. If I have a D7 electron, how I fill these electrons? We are having a totally 5 orbitals in a d orbitals. First, each orbital occupied or accumulate a single electron. Hund's rule says this only. First 1, 2, 3, 4, 5, and next will be the multiplicity is takes place. Next 1, 2. So calculate the electrons 1, 2, 3, 4, 5, 6, 7. So totally I fill the 7 electrons like this. In this manner the electrons are accumulate their orbitals. In this manner the electrons are filled in the orbitals. So this says by the Hund's rule. And next one is the Pauli's exclusion principle. So this Pauli's exclusion principle states thus: the no two electron in an atom can have the same set of 4 quantum numbers. So see here I have a 1s electron, and this is where I have electrons in a 2s orbital, and here I have electrons in a 1s orbital. So I wish to write the quantum number values for 1s and for 2s. Here the principal quantum number is 1, and here the principal quantum number is 2. And azimuthal quantum number is 0. Here also the azimuth quantum number is 0. And next ML, this value is also 0. Magnetic quantum number, this value is also 0. And the spin quantum number S is equals to, here I fill the electron like this, and here also I fill the electron like this, plus half and plus half. But observe here the principal quantum number is change here. The principal quantum number is change. I wish to give another example to this. I have 1s2 electron. In the 1s orbital I have a 2 electron. For 2 electron I write the 4 quantum number values. So these are our 2 electrons. Consider n value is 1. N value is 1 because they are present in same main shell. Yes, L value is equals to 0, L value is equals to 0. And ML value is equals to 0, ML value is equals to 0. Magnetic quantum number same, azimuthal quantum number same, and the principal quantum number same. But what is the difference? Just the difference in spin quantum number. Ms is equals to plus half for this electron, S is equals to, or Ms is equals to minus half for this electron. And the next rule is N plus L rule. So this rule states about the energy level of the atom or that electrons. So see here, if lower the value of n plus L, then what happen? Energy also lowers. If higher the value of n plus L, then what happen? Energy also higher in state. It says about the energies of energy levels of an orbitals. I already told you. So see here, I wish to give one example. 1s is there, 2p is there. So which is the higher energy level? Just I wish to apply ns plus L rule here. 1 means the principal quantum number 1 plus s means the azimuthal quantum number L is equals to 0. So what will be the answer? 1. So in the case of 2p, 2 plus 1 is equals to 3. So which is the higher value here? 3 is the higher value and 2p is the higher energy level. And next see here, if the n plus L value are equal in two energy levels, then what happen? Just I wish to give an example here. 4s, 3p. So see here, 4 plus s 0 is equals to 4. 3 plus 1 is equals to 4. Now observe, n plus L value is 4. Again n plus L value is 4. So values are equal here. Then the principal quantum number says about the energy. So which principal quantum number is higher here? 4s value. The 4 is the principal quantum number. So this is the higher in these two cases. So the 4s is higher in energy level and the 3p is lower energy level. So like this, the n plus L value says about the energy levels. So this is about the n plus L rule. Lower the value of n plus L will lower the energy, and higher the energy of the n plus L value, then higher the energy. If n plus L value are equal, then the energy level determined by the help of principal quantum number. And next concept is electronic configuration. So what do you mean by electroconfiguration? The distribution of electron in their orbitals is called as an electronic configuration. Like carbon having the atomic number 6 means having the electron 6. How these 6 electrons distributed in their orbitals? Like 1s2, 2s2, 2p2. First you have to remember s orbital have the maximum capacity to accommodate the electron is 2, and p has a capacity to accommodate electron 6. D is equals to 10 and F is equals to 14. Means F has a maximum 14 electrons, and D has a capacity to accommodate 10 electron, P has capacity to accommodate 6 electron. So see here, in the case of an oxygen, we are having 8 electrons. So I wish to distribute here 1s2, next energy level 2s2, next energy level 2p 4, 2 plus 2 4, 4 plus 4 8. Totally you have 8 electrons here. So in this electronic configuration, some exceptions are there. I wish to discuss that exceptions. In a chromium and in a copper, the atomic number of chromium is 24 and the copper is 29. Here how the exceptions are takes place and why. See here, I wish to write the electronic configuration of chromium here. Chromium 1s2, 2s2, 2p6, 3s2, 3p6. So 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, and 4s2 20 and 3d 4. Observe here, is this the right answer? No. So how the electronic configuration in chromium? This is Instead of 4s2 3d4, it becomes 4s1 3d5 here, because the half-filled, completely half-filled and completely fulfilled orbitals are more stable than this atom. So the 4s and 3d energy levels are slightly different in their energy. Then the s electron, in the place of s electron, it transferred to the d to give the extra stability here. So here 1, 2, 3, 4, 5. Like this, the completely half-filled orbitals gives a extra stability or a more stability to the atom. So to attain this stability, here this exception will be takes place. As same as in a copper also, 29 is the atomic number, means 29 electron, 1s2, 2s2, 2p6, 3s2, 3p6. Instead of 4s2 3d10, what happens here? Instead of 4s2 3d9, what happened here? 4s1 3d10. So here also the orbitals accommodate a pair of electrons like this, 1, 2, 3, 4, 5. So like this, we got a full-filled orbital here. This also attained the extra stability, and this also gives a more stability to this atom. To attain this stability, the configuration will be changed like this. So this is all about the electronic configuration. This completes your second chapter, that is the structure of an atom. I hope you got a very well information about the structure of an atom by this chapter, and I will come with a next chapter in a next video.